President approved. Can you hear us?
Yes,
Okay, I think we're going live. Do
we
I need to
can't
do
see
anything here?
we can't see your screens, by the way.
But is this live or do I need to do anything or? Yeah, it seems like it's live, right?
Yeah.
Yeah. All right, I think we're live. President approved. Let me share my screen.
Great.
Desktop 2. Yeah.
Um,
You'll be
okay.
able to see. Okay, and then we'll hand it off to you.
Okay, thank you. Sorry everybody for the technical difficulties. Good evening, everyone. On behalf of the Student Leadership Council, we are
Okay,
excited
we're starting.
to welcome you to tonight's event. Behind the scenes look at cutting edge machine learning framework called PyTorch. We're thrilled to have Ali Afzal, a senior software engineer at Meta, here to guide us through a live coding session using TorchRec, Meta's powerful recommender system. Whether you're joining us in person at Weevolt Hall or tuning online, we're glad to have you here. And as a bonus, we have some swag to give away, both in person and for virtual attendees, so stay tuned for that. If you have any questions, feel free to email us at msdsstudentleadership@northwestern.edu. Thank you for being here, and now let's dive straight in. Over to you, Ali Gowani from Meta.
Thank you, President Approved, for the intro there. Thank you to Northwestern University, in particular, the School of Professional Studies, the Masters of Science and Data Science program, as well as its Student Leadership Council, along with some of the academic partners in MSAI and MLDS. So thank you for those. This is a joint event with PyTorch and Meta, as well as PyTorch Foundation and Linux Foundation. So I appreciate all the partners here and supporting this event and sharing more about this. This event actually is part of the Recommender Systems course that we kicked off this quarter. This course actually came about because a year ago, the director of MSDS, Dr. Miller, and Associate Director Beth Lair reached out to faculty asking for different sort of options or ideas on courses. And since I was at Meta, this is what we do all day. And so thought it would be a good opportunity for our students to also learn about this and potentially differentiate themselves in the marketplace. And so this particular course is in its inaugural session right now, and we're in week 8. And week 8 is when we're going to introduce PyTorch to our students. This is the only course that I'm aware of at Northwestern, as well as others where PyTorch is essentially infused into the curriculum. We are tool agnostic, but it's been an amazing partnership with PyTorch. As a matter of fact, they contributed to the curriculum itself. So when we start talking about more advanced sequential learning models and general recommender models, PyTorch and Meta folks had direct influence in that. They shared some of the research that came out, and so we were able to infuse that into the curriculum itself. So it's been great getting feedback from them. And so I do appreciate the students that are currently enrolled, and hopefully many of you will as well and take part in it. With that being said, it's my pleasure to introduce Ali Afzal. He is a software engineer at Meta and is working on a particular library within the PyTorch ecosystem called TorchRec. And so that is something that he designs those for large-scale recommender systems. He focuses on not only maintaining but evolving the TorchRec module for not only internal like Meta cases, but also for open source and community development cases. And so they've been instrumental in contributing to that as well, essentially to build scalable and highly performant modules and systems around that. His work also includes his contributions to Meta as well as the open source community. With that being said, please help me welcome Ali Afzal.
Oh, let's see. Just thanks. All right, so yeah, let's get started. Thank you, Ali, for the intro. The clicker doesn't seem to
We
be
can't see you, by the way.
Oh, you cannot.
Yeah, I'm not sure if there's any. If you can continue, if there's no easy way to fix that.
name.
Yes, we can see you
All right,
now.
awesome. All right. Thank you, Professor Ali, for the introduction. As you mentioned, I'm part of PyTorch TorchRec library, and I'll be talking about the rise of PyTorch, why recommender systems are uniquely uh, hard to train at scale, and how TorchRec solves this challenge in production. And thank you to our sponsors. Thank you to Northwestern University for hosting this event. Thank you to Meta for allowing us to, give you guys a brief overview of what we do here. And thank you to PyTorch Foundation, Linux Foundation for supporting this project. So before we dive in, I recommend the official PyTorch documentary for behind the scenes narrative. It's out, so it goes over like how PyTorch started as an academic experiment and how it became the industry standard for training and productionizing machine learning models. So please do check this out. All right, so what is PyTorch? So PyTorch is a Python first deep learning library designed for researchers, designed for researchers' productivity and seamless production deployment. One of PyTorch's core innovation was its dynamic computation graph. Unlike other frameworks such as TensorFlow or Theano, where you had to define the entire neural network first and then execute it. PyTorch lets you define and modify the model as you run the code. This means you can use normal Python constructs inside your model loops like conditionals, etc., and the graph is built on the fly. PyTorch is very highly integrated with the CUDA kernels, and it's built to be accelerated on GPU. It uses Torch as a backend. So, yeah. All right. So just a brief overview and a timeline of the key milestones here. It began as an internship project. It was initially led by Sumit. He's one of the distinguished engineers at Meta. And they started with like Adam Pasinski and some of the other folks who joined and contributed to it. The goal was to create the flexible, easy to use deep learning library that combined the speed of the GPU accelerated model and the Pythonic way of working. So to accelerate the development and make things easier to for researchers to develop as well as easy to productionize. In 2019, the first in 2018, sorry, Facebook now PyTorch like 1.0. This was the first stable release, and also the integration with Cafe 2, which was the initial Meta framework that Meta released for productionizing the machine learning models. And Facebook itself made PyTorch its primary internal AI, and then we had this transition back in 2019, and then Meta open source the PyTorch, the newly formed PyTorch Foundation, which now is currently managed by Linux Foundation. And then going forward, we were adding VLLM and other, so PyTorch Foundation is becoming an umbrella organization to induce more other open source or orgs that are working cutting edge machine learning. So yeah, some of the key features that are part of PyTorch, which inherently became part of PyTorch like as we moved. So it was initially designed to improve productivity for researchers, but then it became a behemoth in terms of not just researching but also production, as we can see in the next slide. Over the same year, like 20K academic research papers and 140,000 public GitHub repositories cited or imported by PyTorch. That volumes, signals just popularity, not just popularity, but a robust knowledge sharing loop, like papers or papers and production feedback loop that. Um, so yeah, beyond just that, PyTorch is deeply embracing the community aspect to it, and it promotes the culture of design docs, RFCs, and like full research cycle to production setup. So, and how we can make this any type of framework from inception to deployment faster. And we have like plenty of examples. And after the induction into Linux Foundation, Meta is not just the only company that's maintaining PyTorch. We have like AWS, Microsoft, and all these other organizations join. So it becomes a larger project. And so here are some of the achievements of PyTorch based on the current dynamics. We have like flagship models like GPT-4o, Meta's Llama 3, not even Llama 4 as well. Stable Diffusion, Tesla's Dojo. I initially saw this talk from Andre Karpathy, which I initially had the code on the first slide from. And so they started, and he was, I think that was back in 2017, and that was like the starting point where it was validated, even if the PyTorch wasn't released, but it was being used by all these big organizations, including Tesla, to train their framework and embrace it. So beyond what's happening after the release, we have PyTorch 2.0, which introduced Torch Compile. It's used in many different models, but essentially made for recommendation systems and other models to improve efficiency and to improve the training cycle and cut the training cycle by half. It also unlock the ahead of time graph capture and increase the speed. Yeah. So now I want to transition to TorchRec. I've given a brief overview of how PyTorch has transformed the scale in the machine learning landscape. And so now I want to shift it towards TorchRec and like what is TorchRec and how TorchRec came into being and why it's one of the state-of-the-art infrastructure, you can say, that is used not just by Meta and some other big companies to train their recommendation systems model. Before we talk about TorchRec, though, I want to give a brief overview of what recommendation systems are and how they work. So they're just basically algorithms they're just basically algorithms for that personalized content for users. Recommender systems basically sift billions in options to surface a handful a user will love, personalizing at a very interaction layer, and they predict they predict the user pattern and why that user pattern prediction is necessary. So recommendation systems are usually and that is the thing of a past now because a lot of small companies are coming in as well, but they were usually the thing for big tech to increase their revenue growth and add more users to their user base, and and so that's where the recommendations, even in today's landscape, right? Even if you know it or not, recommendation systems are everywhere. Like if you consider, if you watch a small short video on TikTok, right? You're thinking that you're engaging with that video on whichever level, but if you look at the flip side, you're just giving them your time, you're giving them your likes, you're giving them your comments, and they're basically trying to capture all of that information and to figure out, what type of content you like. And that's basically where recommendation systems are. And so beyond this, just to give you the impact that they play today in our old, like 35% of Amazon sales were actually made by using recommendation systems. Like when you log in, you see, things to purchase and relevant products that you see on the Amazon webpage. Also, same as YouTube or other Netflix or other video platforms, like it gives you options that you may like that you want to click on. And with YouTube, you can see that it's about 80% of the content that was watched on YouTube was what was actually recommended. In today's landscape as well, we look at Meta Reels, TikTok, and a bunch of other content platforms. They're like super engaging just because how good their recommendation systems are. And so far beyond the big tech, like banks and other financial institutes, it's used in education to figure out, what courses a student may take. It has advancement in healthcare industry, specifically used for radiology images, like triaging radiology images to different hospitals, and in framing recommendation system as a horizontal, sorry, horizontal problem that shows why audience like how TorchRec plays a big role in in the recommendation system space. So we talked about recommendation systems, and now that we know that what they actually do, but like what's the problem that TorchRec is trying to solve? Like what is actually that we're trying to figure out, like, which is like what the hard problem right here. So number one is that the sheer size of data. Like in general, the model, like if you're training your data on a simple model, it's like a linear layer, right? It's like a small neural network. The model is actually very small. But if you look from the perspective of recommendation systems, the model becomes huge. And why it becomes huge, I'll talk about in the later slide. But just to set the stage here, this is an example of a two-tower model, which has a dense arc and a sparse arc. So basically, sparse arc makes the model so huge. And that's where you would need TorchRec to give its parallelism constructs to help distribute that model into multiple layers and speed up the learning process. Also, the other bigger challenge is that sparse arc is also accessed sparsely. For instance, like you have the example of if one user watches like 10 videos, right? And then so user item would be that you have it as a dense arc, but those 10 videos or like similar to those 10 videos, like if you have like one category, you have like millions of videos in that one category, and then you have like hundreds of categories, 100x million, it's a big. And then so interaction is very small because you have to recommend just for one user. And so you've got the user ID, but how would you recommend it? So in say two-tower model, you do dot product, but again, the challenge is big because the embedding size is big, and embeddings is what represent those movie categories, which you can also call features. And yeah, data mix and memory is also a constraint, which we would see why that is. So essentially, what is TorchRec? So TorchRec is basically whatever PyTorch isn't. So it's an extension to PyTorch. It's the PyTorch first library. It's part of the PyTorch domain for building, training, and serving large-scale recommendation systems. As we talked about, it sits on top of like regular Torch. So you can use all the data structures and distributed primitives that's PyTorch already presenting. And it uses those high-performance kernels for Rexes. Engineering normally have to, which, for Rexes, which you normally have to re-implement, you can use PyTorch, you can use TorchRec. So TorchRec also introduces the concept of data model parallelism, which we're going to talk about next. So yeah, the question now here is, why do we need parallelism? If you look at this slide here, you can see that in a normal space, you have the CPU which can do 100 gigaflops per second, and you can see that the RAM, which is the memory that's close to CPU, you have quite a big option here. You can go up to terabyte, but there's no like inter-device communication because in some cases you have like one huge CPU. But if you look alternatively in GPU space, right? So you can basically 10x what you were doing, at least 100x what you were doing in CPU. You can change that from gigaflops to teraflops. The GPUs are super fast, but there's a drawback, right? GPU only has 10 gigabits, or in some cases 80 or 100 gigabits, right? Even if you go to A100, which is like one of the most powerful offerings from NVIDIA, it's up to 80 gigs of memory. And it's called HBM, it's high bandwidth memory. The reason it's called high bandwidth is that because it has a very faster GPU to GPU communication. As you can see, it can go up to 10 gigabits per second in the multi-GPU domain. So if you basically distribute if you come at a crossroad where you actually need to distribute your model, that's one of the reasons that you would need that you would need all these distributed primitives for training purposes and even for inference purposes. So I talked about model parallelism. Now let's review what model parallelism actually is. So if you look at this slide, you see those two blocks and consider those two black boxes or consider them as models. And so what happened here in this slide is that you have device 0, which is GPU 1, you have device 1, which is another GPU. And what we've done here is that we've distributed, so these like colorful squares, these are basically data or model. You consider them as models, and you have distributed that across two devices. And so first you get your batch of input data, which you want to train your model on. And so this is the first communication that happens. So this is like in neural networks, you have like forward and backward. You guys are familiar with how neural nets are trained. So in your forward cycle, what you can see here is that your data goes through device 0, and then it goes through device 1. So that's where you have your data distributed across, because the distribution it has to be in sync. So your data goes through device 0 and then goes to device 1, and then it goes to device 0 again. And then you apply your loss or optimizer function, loss and optimizer, and then you have a backward pass. You can see it's the same. So it has input disk where you would distribute the data, and then you would have compute cycle, where the compute cycle generally in this space is looking up the embeddings, which I'll talk about next, what they are. And then and then we have an output disk. So you have this in this one forward cycle, you have these 3 steps. And if you can look at here, you have like 4 total communication comms cycles that you had to do. And this will be an important point in the next slides. And then you run backward and you communicate, and then you go towards step 2, and that's how the training works. Now let's look at what data parallel is just in terms of comparison. So we talked about model parallel. Now let's look at data parallel. So in data parallel, what essentially you're doing is that you're copying the model. You're not distributing it. So again, that black square, that's a model. So you're basically distributing it on 2 devices. You're basically actually training 2 separate models, if you can consider. But there's a neat trick, which I'll show you how the training is distributed. So data is distributed. So you have like batch 1 and batch 2 in 2 different devices. So you got like big chunk of data. This green thing that you see, that's batch 1. And then, it's divided. So those are in different batches, and it goes through your, forward pass and backward pass. And you apply your loss optimizer, it goes through the backward pass. Now, the neat trick here is, and that's why you can train like models with huge amounts of data, is that so you do a comm cycle basically where you would average out all the gradients before you update those gradients. And that's how you can train larger models like llamas and all these other models that you see generally. And that's what data parallel is, right? It's basically keeping the model small, but you have large and huge amounts of data which can be easily distributed. And one thing that you can notice is that there's only one comms between GPUs that needs to happen. So you have less overhead of GPU to GPU communication, and then you can train larger data. And so how our recommendation system different? So before I go further, I want to introduce these 2 components that are part of TorchRec. So there's a planner, and then they're different. There's a shardder which supports different sharding type. So planner, what it basically does is that it takes in all your hardware specifications, right? Like what do you have, like how many GPUs do you have? It takes in all your input data and looks at what type of data that you have and takes in all your tables, embedding configs. And it basically spits out a plan to give or to tell the CPU how to shard the model, how to distribute the model. And so some of the sharding types that are supported with TorchRec is, so one type is table-wise. So what table-wise is that you basically have one table. If you have one table, you just pick whichever device you want to pick. And if you have more than one table, then you have the option to split them. But that's what essentially table-wise is. Now, you have column-wise and then you have row-wise. So column-wise is basically splitting data in the column dimension. You split it and then you distribute the data on to different devices, and then you have row-wise. Row-wise is just basically simply the splitting up how many rows you want to keep on one device versus the other, and that's what row-wise means in this context. And this basically plan is generally designed by Planner. And that's one of the major components of TorchRec. And so this is what's essentially used in the model parallel space. And we also talked about data parallel. So in data parallel, you're basically essentially copying the model. As we saw, it just goes into both of the devices. So just tying back in everything together and, what we actually use. So we saw the example of, so let's look at what no parallelism looks like, right? So you have your input batch, you have your model, and then you have your optimizer loss function, you do your forward, backward pass, update gradients. That's how it works. Now, if you go towards the data parallelism example, we saw the batches, the data is actually divided, your model remains the same, and then you apply the optimizer, you sync the gradients, you're done. Now, what TorchRec essentially uses is best of both worlds. We know how to distribute. We're already part of PyTorch. Why? So we use that data parallel primitive, and we also apply the model parallel primitive as well. So what it looks like is that you basically divide the data in batches, and then what you also do is that you also divide the model, right, inside across different GPUs. And then you train the cycle, and that's what we found to be very useful and helps train large-scale models. So let's talk about what's actually happening here. So generally, so TorchRec is not very intrusive in that, so basically you'll build your model with however many layers, and then you would also set your embeddings. And so what we essentially do is that we basically we want the modeler, whoever's designing the model, to do as less changes as they can. And so that's why we've designed some of our constructs like so embedding table config, which takes in two so embedding table config takes in two types of config. So we have embedding collection. So collection is just like a group of embeddings that are together. And all what we do is that we convert those Torch related embeddings into TorchRec specific embeddings. And that's all you need to do. And what you basically do is that you would pass your trained model, you pass it to distributed model parallel, which is the TorchRec API, which basically looks at what to shard. It basically does that itself, and then it generates the plan itself on how to shard the data. And then yeah, let's move forward and see how it happens. So we talked about how TorchRec is a combination of both data parallel and model parallel. So if we have a data parallel layer, we first acknowledge that we first look at what layers that are included. If there's a data parallel layer, we first add that to the model. Then we see how the table is sharded and what layers are included. So what specification is included for that specific model, and then we basically shard the model. So this is like an example of like table-wise sharding, as I initially talked about. So in this case, we have three different embedding tables, and we've distributed across two GPUs. So let's look at again, let's have everything together from what we know and see what actually happens in real time. So we have the data, we divide them into batches. We talked about, data parallel. And then we talked about we have a forward pass that we do. then we have a backward pass. And so in the forward pass, you would notice one thing here is that, there's a lot of communication happening here. So even though we talked about, how model parallel is great and you have like huge embeddings, you have like sparse data, and you can easily, distribute your model so that, you're faster, but the overhead is now communications, like that kind of slows things down. So it negates the purpose of, using the model. So let's see how we're solving it. It doesn't negate it, but it's a challenge, right? So and then you have to choose, should you like try to shorten the model or try other optimization primitives? Why do you actually need to use model parallel? So yeah, let's talk about communication. So how do we optimize it? So to optimize the performance, we use the TorchRec specific primitives that we've designed. So on top of Torch Tensor is an n-dimensional array. So what we've done is that we've introduced jagged tensor. So what jagged tensor is that if you consider, say, a city block, and you look at the skyline and you see the building's height change, right? So consider one city as a one-dimensional array, but like some of them are shorter. So those shorter ones, like different height ones, and that's what jagged means in this case, right? So you have this, like these sparse embeddings. One feature would have like 100 IDs, but other feature may only have 10 or 20. So what we've done is that we've basically taken that jagged tensor, we've converted the PyTorch tensor into jagged tensor, and the benefit of that is that we've converted that into one-dimensional array, and then we say stores lengths and offsets in it, so that there is not a lot of overhead by like filling up the dimension or metrics, and it kind of saves a lot in terms of communication, what we have to communicate. So key jagged tensor is basically adding one more dimension. So jagged tensor only represents like one feature. But the key jagged tensor, you have the key. So you have like feature one, say your user IDs, your item, any item, your movies, or whatever features that you have. And they're jagged tensor, so they're two-dimensional representation in 1D, basically. So that's what KJT is. And then so key tensor is the output of the output dist, which we just talked about, forward and backward pass, and then what's happening before, after the like in the forward pass is that, you basically distribute the data, you look up the embeddings. So you've got some IDs, and then you look up the embeddings from there. And so these embedding lookups are basically the key tensor's output. So what key tensors is, again, similar to what key jagged tensor is, but these are key tensors are two-dimensional tensor, but with a key. So for each feature, whatever we've looked up, right? And that's what key tensors is. So it's a feature and a two-dimensional tensor. And so this basically cuts a lot of overhead and compress things down a little bit. So let's look at the next thing that we've done. So we've also, so PyTorch already uses kernel level operators to accelerate, because we just talked about, how PyTorch is accelerating using its own C++ there. And we use PyTorch, we use those PyTorch primitives, but they're still slow. And why they're slow is that because in the Rexus space, in each cycle, what you would essentially do is that you would look up those embeddings, and that's what you're doing for each separate table. Now, we analyzed that, and we looked at, how we can speed things better. And there's another open source library from Facebook as well. It's called FBGen. It's a matrix multiplication library. It's an accelerator that accelerates the mathematical aspects of tensors. So we've generated a kernel which like bash things up together into which was bashing together into one cycle. So for instance, if say you have to look up embeddings for one table, now you're not actually looking up embeddings for one table. You've grouped like you have grouped those like 10 tables. You send it to table bashed embedding module, which is introduced by FBGen, and then you basically look up all the embeddings for all the tables in that bash that you've gotten. So you don't have to communicate every time now. You just only provide the full batch, and you would get all the embeddings. The other optimization that we've performed is combining the backward pass with the optimizer. Traditionally in PyTorch, we calculate all the gradients and then apply the optimizer, but this leads to additional kernel communication. Going back to the example of in your forward pass, right? You've looked up those embeddings, but in your backward pass, if you so before your backward pass, you're applying your optimizer layer. The optimizer function tries to look up a certain embedding. The cache is so small, you get a cache miss. So and that's why we fused it. So basically, you do your forward pass, you calculate your optimizer value, and then we do the backward pass together in the same. Yeah, feel free to go to that link, and it has more detail in how this works. So another aspect that we've, and this directly ties to the communication problem that I've talked about, and I'll tell you what this thing is here, is that the GPU execute work in order that's issued, just like a CPU. It's a sequential one kernel time, like scheduling on So what we've basically done is to overcut this communication problem, is that pipelining thing. So this is basically a GPU trace in real life. And this is what it looks like. So it has, if you can see this clearly, I can zoom it in if you can't. So it has like an input distribution. Input, and it has a compute cycle, and as well as, where's the compute cycle? The slide is too small, so I can't see here. All right. Right. So you have the input disk, you have the compute cycle, and you have the output disk, separated out as like in sequential pattern. So this is what we have done. So we've pipelining things, and basically we've overlapped the communication. And so the benefit of that is that as we're using different multiple streams to do other work, we can, because GPU has multiple streams, so we can utilize those streams to help increase the training. And what does that matter? So first look at what we're doing. So we have this extra compute available. So here's the interesting part. So this is B+2, right? So basically we're running 2 steps in advance. So we first got the input batch, and as you can see, so we copy data to device, you move forward, and then you can see we're already doing input disk and pipeline for B+1, so batch +1, versus if you look at in the previous trace, we were just doing input disk for batch 2. Again, like all the steps like in cycle, and this is how pipeline has improved. We've used the communication delay and added some compute layer on top of it, so to help train. And it's saying that if you've improved it by 35%. What does that actually mean? So 35% actually means you're getting faster developer velocity, you're getting lower cost, right? Because you're still running the system for the same amount of time. Then you're getting better developer velocity, you're training faster, your inference is faster, and then you can reiterate on that faster. Or if you're training certain models, you can we generally measure the QPS, which is like how fast you can look up those embeddings with what rate. And so you're just basically saving cost, as well as helping the modeler to develop faster, to reiterate faster, and be more efficient. Now let's talk about why TorchRec. Why I've given that speech. So TorchRec has it's battle tested. It's used at Meta, widely adopted in production. Facebook has trained Facebook newsfeed, Instagram, and all these other big models. And there's a lot of research that's happening on this side. And one of the new and upcoming sharding type, that sharding parallelism, which I haven't talked about, is 2D sharding, which is a new up and coming, and it helps train not just on tens of GPUs, but hundreds and even in thousands of numbers of GPUs that you can use it and distribute it. Databricks has it as an offering. It allows their users to use it for training their recommendation system models. When the Twitter RecSys model released, the model code released, we found out that Twitter is also using TorchRec for training their models. And there are a lot more other companies that are using TorchRec, but we can't actually see because it's an open source and nobody wants to, give their secret sauce on how they're, because like it's kind of bread and butter, it's giving them revenue. So, and the reason we think that a lot of companies are using it because these primitives that we've built, it's taken us years and they're really hard problems. They're not easy problems to solve. We have partnership with NVIDIA. They've recently published a big change to our repository. They've introduced hierarchical key value store. And Alibaba Group just reached out to us recently. They have another offering called Torch Easy Rec. This is their offering to their own cloud for training recommendation system model. But Torch Easy Rec basically underneath uses TorchRec. So there were certain gaps that they want us to fill for them. So it has some validation in the industry. If Meta is not enough, we can see that a lot of other companies are using it. And this is not such a great measure if you want to compare different RecSys frameworks, but we've also are state of the art and have the highest stars in terms of RecSys space. So if you look at TensorFlow recommenders, we've beaten them recently. But yeah. And one of the other reasons that TorchRec is really the state of the art, or really the library for future, is because it's actively in development. This is basically the chart of like the commits happen over time, and you can see that TensorFlow, I'm sure Google is developing things inside. They're not releasing, or they're not very active. In the open source side, you also have HughesCTR, which is kind of not as active recently. But TorchRec, it's just the beginning of this year, but we have a lot more things that are coming up. And yeah, feel free to join the community, contribute if you can. We always welcome outside contributors. There's a link you can go in and look up and how to contribute. And if you have any questions there, please ask. If you're training something, yeah. All right, I think so. I have a little demo that I've prepared. So let me see where that is. Is it here? Okay, I can't see it there. Like, I'm not sure what I'm going to present. So
We can see it.
right. So all right, so basically this demo goes over like how some of the general primitives work. So this is not a very conventional or how TorchRec is used type of demo. This is basically how some of these components work and what the output looks like. This is a full end-to-end demo, so it also includes Sparse, which is what TorchRec is used for training, but also has a dense layer, which has its own optimizer that you guys will see. So these are instructions on how to set this up. This is an example on Google Colab. All right, so here you're just basically setting up the environment, like what type of device you want to use. For GPU communication, Nickel is Nickel is the library from NVIDIA that we or everyone essentially uses if you're using NVIDIA GPU. But for instance, if you do not have access to GPU, you can use Glow. I can add it there. So Glow is a library for CPU communications. Okay, so generally that's what you usually do at the start. You configure your model. You basically define your hyperparams. You have other parameters that you want to use inside the model. That's what you essentially do. Now here's what I talked about. You have to convert your embeddings into something that TorchRec can understand, and that's where the embedding tables and config is defined. So I think the embedding back collection config is here. So you basically build your configs and pass it belong to it. And this is what you see what an embedding back collection looks like in terms of as a model graph for the embedding back collection. So moving forward, so here basically, this for. Okay, so this is basically spitting out a plan. So what is happening here is that first we have set the topology, basically what device that we have and how we want to like what we're using. But our planner that's for TorchRec, it's very smart to looks at topology and figures out what type of sharding is important. And in this case, we have resort to row-wise. I can see that. And so we've also passed that model to model parallel API, which I initially talked about, the importance or the bread and butter of TorchRec. So you've basically created a separate NN module, which is embedding back collection, which is what TorchRec understand. But essentially, you would wrap it in a different, your own model, or you would have like a deep learning DLRM or some other model. And so you would pass that instead of EBC, but generally, if you're just training your embeddings, you can also do that. And then you can see the model graph. It looks like it's wrapped, your embeddings are wrapped across the distributed model parallel here. And so what's the step? So here, basically, we're designing how you're loading your synthetic data. So synthetic is because it's like I'm just using random data, but you can actually plug in any data here. You just have to do some feature engineering to figure out how you want to set up your embeddings. So here's a function that's very important part here is how you're coalescing your key-jagged tensor, coalescing your tensors into or transforming them into key-jagged tensor KJTs, which becomes the input, which we talked about. It's one of the optimizations where we help compress the data into small form. And just as normal, you would have your training set, you have your test set, and then you have some reshuffling of the data so that you don't overfit for that purpose. Now, what's this? Let me see what's on. Okay, so here's your defining your dense layer. So this is where the NN sequential and the dense part of the data. So here I'm generating using the sequential. I'm generating one or two, I guess. The linear layer, adding it, and basically defining what the dense arc would look like. This is going to be separate from. And yeah. And so moving forward, we have our training loop and how we want to evaluate our model. And so the training loop and is just conventional how you would define things in PyTorch. We can share this link as well. So if you guys want to deep dive into how this is designed, and then you have your training loop, how you want to train your model, each step as we talked about. And then so for each training step, this is the output that you get. You can look at your evaluators as well as, as for each epoch that you train, and then eventually in the end, you can get your output. Yeah, but this is like a very quick and short demo of like some of the components that we have built and use in TorchRec. Yeah. All right. Yeah, I would like to introduce Bethany to be here.
So I get just to show our appreciation for Ali for coming in and for giving his talk. The school and MSDS program that's got this small. Program. Thank you for bearing with us. Thank you for all our attendees, both viewers online and in person, for bearing with us with our tech difficulties, different laptops, different systems, different, restrictions and permissions were needed. So I don't know if there's any questions online or in the room. I can open that up. We have a couple more minutes if you want to show that. And then if you can go back to the PowerPoint, there is a final slide that just has a QR code and a survey that we ask all participants to kind of fill in today. Of course, you can mention the tech difficulties and starting late. We acknowledge that, but the talk was still worthwhile. So thank you for coming.
We have a question about the TorchRec notebook and access to slides.
Share that. Yeah, if you send it to me, I can figure that out. Share that with you.
Yeah, yeah, I think we can connect on LinkedIn as well. So if you have any questions for the demo, we can talk about it
Yep.
further. Yeah.
Yeah, we'll figure out, President Pro, we'll figure out a way to share it. So we'll take care of that.
A quick question. What, like, well, from your experience, what are the top 3 factors and features that, besides what's next on the out or that you for the user and Instagram or Facebook?
I think that's basically designed by the model, right? Like how you design. So there are different models that work differently. So if you go back before in the initial times and you have collaborative filtering or content-based filtering, right? They work differently versus what I showed, which is the 2-tower model, which takes in dense and sparse. So whenever a request comes in, right, and it basically has to fetch that dense and those like small sparse embeddings and do a dot product. And based on dot product, you get the closest things that the user would like. So that's essentially what's happening underneath.
Not to jump in, but this is exactly what you will learn in module 10. If you
Sure.
take the recommender systems course. So very exciting, some of the leading edge stuff that Ali's talking about. That's very pertinent in today's sort of ecosystem of recommender systems.
Yeah.
Yeah, so very impressive work. I wanted to ask a little bit about the jagged tensor. So I know that's like a wrapper around the tensor module, right? So I'm curious, how do you reconcile something like that where you have different offsets, variable offsets and things like that?
Right.
Especially with sharding as well as kind of the dot product computation. How do you manage to have the jagged tensor kind of exist, right? Because that's like
Right.
variable different.
I think that's where the concept of their parallel comes in, right? So first you're distributing data in your batches. So now you're just limited to that aspect of data. So you're kind of already distributed that aspect. So and then I think one of the reasons so it after the distribution, now you can fit everything into the memory or into the model because that's what it accounts for, if you can actually train on that GPU or not. So once you've limited the search space or once you limited the space or distributed it, I think then it makes things more easier. Then it's up to you on how you want to evaluate or transfer, do whatever with that data. And I think that's where the jagged tensor comes in, where you pick up that's like not consistent and you transform it into a very consistent way, which is like the jagged tensor is just like a one-dimensional array. It has its offset. So for instance, if you have a tensor here, you have 1, 2, 3. So these are just arbitrary values. So this is what like a jagged tensor would look like. So for instance, you have a two-dimensional vector, and then you would represent the length here. So this is like, say for instance, if this is 2, 0, 1, something like that, right? So these are the lengths or offsets. So for instance, first feature is represented by these two, second is represented by this, or third is represented by so it's 0, so you'll skip that and you have 1 here. So this is just basically the idea. Yeah, feel free to look up TorchRec and go into, like, there's a very big note on how jagged tensors help, and I think it gives you more with some good examples on how it actually works.
Thank you. And I have a follow-up really quickly.
Yeah.
So I know like graph recommender systems are also kind of getting more popularity for like especially knowledge graphs and things. Is there any like future plan to implement that in, or is that kind of like community driven?
So I think TorchRec is used for training and productionizing. So it has like an inference and training concept. How you mold your model is up to you. So it kind of gives you those primitives. And what it helps is in like, training with sparse. So generally in a smaller different models, right, you have your linear layers, you have your sequentials and a bunch of other stuff. But in case of recommender systems, right, your sparse becomes your model because embeddings are part of model, and that's why you need that. So if it's graph or whatever thing that you want to train, you just have to figure out how you can fit that on top of TorchRec to get those primitives to work for you.
Okay. Thank you.
In data parallelism and model parallelism, are the models distributed across GPUs?
So in model parallel, yes, that's model is.
Data parallelism?
So data parallel is what data is distributed. Model is different, right? So in model parallel, so in combination, you would distribute both, but in general, in data, so in data parallel, the model remains the same. That we saw that, the model was replicated across both of the GPUs. In data parallel, we saw that, but in model parallel, we saw that we actually distributed the model as well.
Separate.
Yeah.
So isn't the memory limited with the GPUs? Like if you load the complete model into the GPUs with the.
Yeah, I mean, there's a lot of we like this is a very big problem, right? We see a lot of OOMs, which is like out of memory calls, when you're training large scale models. So this is something, and it's not just the combination of how you shard, it's also a combination of the size as well. Yeah, so this is not a fully solved problem, but this is one of the best way to resolve it. Yeah.
Could you go over how the embedding lookup speed up happens? Do you load the entire embedding into memory, or do you
Yes.
cache the embedding? And then...
Yeah. So the first step is so before the input is you have the sharder. So when you call the sharder, so whichever sharder you pick, when you call to device, what it basically does is that it first distribute the embeddings onto GPUs, and then in the train cycle, you have the data come in and you have the IDs inside that data, and that's how you look up, right? Yeah. So first, before the training starts, you distribute the embeddings. Yeah.
And follow up on that, the sharder is the CPU deciding how the sharding happens, or?
So that's where the planner comes in. So planner basically takes all the topology, whatever's part of your system, how many GPUs, and how many tables and things like that, and it basically picks up what the sharding plan would look like, how it needs to shard.
Data parallel training, like how do you combine the results of each model? So each model is separately trained on a subset of data. How can we combine the weights and get them?
So that's one of the quick trick that I talked about, right? So for after the forward and backward cycle before the gradients are updated, you basically do a communication cycle where you average out the gradients before you actually update them. And that's how you train a larger model using data parallel.
No more questions online, and then we're done here. So thank you again, Ali, and thank you again for all our viewers and participants.
All right. Thank you.
And don't forget to fill out the survey while you're here. You guys cannot leave until you've seen all of your phones out and you scan that QR code. I will lock the door.
Chance to win free swag as well with the survey link. So please fill it out. Thank you.
Thank you.
It's small, so I can be here.